Today we're investigating radioactivity and in particular radioactive decay. So we're going to simulate some radioactive decay with a dice, and our safety here, throw the dice gently and wash hands thoroughly afterwards because of the surfaces that they've been on. And so the first thing is we're going to start with 100 dice. Make sure that you have exactly 100. Place it in a cup a bit larger than the contents of the dice. Put your hand over and shake well. Then you're going to scatter the dice on a large area, for example, a portion of the floor. And before you do the next part, set up your data table with which throw number it is versus the number of dice left. So you'll start with throw 0 and the 100 dice, and then off you go. Pick up all the dice showing number 1 on the top face. Count them and put them to the side. Now subtract this number from the number that you rolled and record the subtracted number. And just here looking at some of the ones with number 1s on. And then pick up all the other dice that didn't have 1s on, place them in the cup, reshake, and roll again for trial throw number 2. And keep recording your data by subtracting the number that you've discarded, and repeat the shake, roll, count, record, discard the number 1s until all the dice have been discarded, every single one. And we'll just have a look at a video of this activity.
Do it again. Lots of 10 might work well.
I have a red die. Who puts a red die in a green die box?
Well, you know what they say about dice.
No good.
Actually,
Because she's smart.
There's a hundred
Overflow.
I have this.
Well, give that to me. Maybe that doesn't work.
See, I was right.
I'm guessing you might need it. No, maybe not. We'll see how it goes.
Minus 14. Minus 15. Minus 16. Thank you. Well, it should be backwards, you said, right?
Pardon?
I should go 41, 40.
No.
Start.
As I put on the board.
First throw.
And what we're interested in is how we're going to analyse the data. Now, plot a graph from your data or use the data on the subsequent slides. And you're going to plot the total number of dice rolled in each throw, vertical axis versus the trial number, the throw number on the horizontal axis. And if you've got more than one group that's collecting data, you're going to plot the sum of each trial for all of the groups, and that's what we've got. So make sure you pause the video as you are extracting the detail from these charts. So here's the first one, and it just does the first 15 trials, and you'll actually see that with 5 groups we start the total of 500 and we go down to 27. And then the next of the 15 throws, a couple of the groups are down to 0, but not all of them, and you just have to keep throwing and writing the data down each time, even if you have the same number of throws on successive trials. And this is the data as it was collected by the class. Slightly easier maybe to see the tables that are there. So what's the shape of the graph that you obtained? And what does the shape mean? What's it telling you about the number of ones that you had, the remaining dice, versus the number of throws that you've had? So we're going to look at that data a little more closely to analyze it further. So to start with, look at 2 places on the curve of the graph. And so, for example, record the number of throws that you took for 250. Go as close as you can, because not all the numbers are exact, and sometimes you might have to put half a throw to get that, but I will leave you to look at what is needed. Now compare the number of throws for 125 dice remaining. So you're halving the number. What's the difference between those 2 numbers of throws? Now, repeat with 200 dice compared to 100, and again, look at the difference in the number of throws for 200 dice and 100 dice. And finally, choose 2 other pairs of dice where the first number you choose is double the second one. Now, how do the number of throws differ when you do that subtraction? So, what does it mean? And as you're looking at it, you may see some similarities. If you've rounded up or rounded down too much, it might not be quite as obvious, but there are certain similarities. So, regardless of the number of dice you have, it takes the same number of throws to get to half that number. Now, how is this going to model radioactive decay, where you have a sample of an element with a particular number of nuclei radioactively decaying into other atoms? And remember, not all isotopes of all elements are radioactive, so we're only looking at the radioactive ones. So how does it model it? And we've got a diagram here. Start off with an original mass, and after a particular time, there's 50% less. It doesn't mean half of it has disappeared. It's just converted into a different material. And so after the second half-life, you've got 25% left, etc. And so here we're asking how long will it take to get to 1/8 of the original material? That's your 12.5% that is left. And the T1/2 between each interval is the same, your half-life. It's the same for one isotope of one particular element. Each element, each isotope will have a different half-life. And we're going to look at one example, somewhat interesting one here, of carbon-14, where it decays into nitrogen-14, and in simplicity, just going to put a beta particle, which is an electron. And with a nuclear equation, when you look at the atomic masses, the superscripts there, they have to add up to the same on both sides of the arrow. And ditto, the atomic numbers on each side of the arrow have to be equal, which indeed they are. And looking more closely, we've got the nucleus of the carbon-14 atom, which has 6 protons and 8 neutrons. And it's by radioactive decay turning into a stable nitrogen-14 isotope with 7 protons and 7 neutrons. So the nitrogen has 1 less neutron but 1 more proton. So what has happened, we're converting one of carbon's neutrons into a proton. And with more protons, it can't be the same element. No, it isn't. It's now nitrogen. And what we're looking at here is, you can see the nuclear particles there with the decay, negatively charged electron being produced, as well as the nitrogen-14 nucleus, and an anti-neutrino. So not everyone needs this particular slide, but it's interesting. The nuclear particles are made up of quarks. The neutron, 1 up and 2 down, U's and D's. And the proton is made up of 2 ups and 1 down. And you're producing an electron, which is negatively charged, and the anti-neutrino. So if we're looking at carbon-14 and its half-life, samples containing carbon, often relating to living things, they have a really tiny amount of carbon-14 in them, but it's constant as the plant, animal, algae is living. Maintains that carbon-14 percentage, but when it dies, the carbon decays and the proportion of carbon-14 reduces, and that reduction allows us to identify its age, because the half-life is the same for each reduction in half the amount of carbon-14 that is present. So 5,730 years for half of the carbon-14 to disappear. For it to go down to a quarter, twice that, 11,460 years, 2 half-lives, and 3 half-lives and 4, etc. When it gets to getting on to 40, 50,000 years, it's harder to be accurate with your assessment of its age. And carbon-14 is really staying pretty constant for the living things to maintain their proportion, and that is because of interactions of cosmic rays with the atmosphere, and they're going to break up atoms, and some of the loose neutrons collide with nitrogen atoms, making more carbon-14. And going on to an activity to look at some other elements, a whole variety. Some half-lives are seconds and minutes, others are multiple years, and you can look at the ones here. And what you need to do is to research and add 3 different radionuclides and the decay, half-life and energy details, one producing an alpha particle, one producing a beta particle, and one producing a gamma ray. And often with the decay of elements, it occurs in a series. So for example, for uranium there, the first decay is that of an alpha particle. And then finally, many thanks to Washington International School, their Team Science, and Mr. Godwin's IB Physics class.